Hey there, it's Shannon Math Chick Myers, and today we're covering section 4.2, Reduction of Order, from the ZIL Intro to Differential Equations text. So in our last section, we learned that the general solution of a homogeneous linear second order differential equation, which looks like this, a2 at x y double prime plus a sub 1 at x times y prime plus a sub 0 at x times y is equal to 0 is a linear combination where y is equal to some constant times one solution y1 plus another constant times some other solution y2. So where y1 and y2 are solutions that form a linearly independent set on some interval I. Now we will start checking out a method for determining these solutions. When the coefficients of the differential equation, the same one that I wrote before, are constants. This method, which requires algebra, breaks down in a few cases and yields only a single solution y1 of the DE. The idea in this section is that a2 at x times y double prime plus a1 at x times y prime plus a0 at x times y equal to 0 can be reduced to a linear first order differential equation by means of a substitution involving the known solution y1. Then we are able to find a second general solution once we solve the reduced differential equation. All right, reduction of order. Suppose that y1 denotes a non-trivial solution of this equation we've been working with, and that y1 is defined on an interval I. We want a second solution y2 so that the set consisting of y1 and y2 is linearly independent. In section 4.1, we learned that if y1 and y2 are linearly independent, then their quotient, y2 over y1, is non-constant on the interval I. So what do we have? We have y2 at x over y1 at x is equal to some u at x, or equivalently, y2 at x is equal to u at x times y1 at x, which is that known solution. The function u at x can be found by substituting y2 at x equal to u at x times y1 at x into the given differential equation. This method is called reduction of order, since we need to solve a first order DE to find u. So let's check out our first example. The indicated function y1 at x is a solution of the given differential equation. Use reduction of order to find a second solution y2 at x. All right, so let's crunch out some derivatives, do a little bit of algebra, and scope out what we have. So we have been working with the idea of our substitution, that y is equal to u at x times y1 at x? Well, y is going to equal to u times xe to the negative x, because y1 at x is given as xe to the negative x. Good so far? All right, and now going with y prime, u is a function of x, so y prime will be, I'm just going to do, if we have three factors, so you just have to have a sum of three terms where on each one of them's been differentiated. So we'll have u prime times x times e to the negative x plus u times 1 times e to the negative x plus u times x times negative e to the negative x, just using that extended product rule. And then writing these together, I'm going to factor the u prime and the u out to the right. There's only one term for the u prime, so we'll have xe to the negative x times u prime plus 1 minus x times e to the negative x, and then times u. Cool so far? So now we need to find y double prime. So again, we have three factors, so 1 times e to the negative x times u prime plus x times negative e to the negative x times u prime plus x e to the negative x times u double prime takes care of this first term. And then the second term we have plus negative 1, that's the derivative of 1 minus x, times e to the negative x times u, plus 1 minus x times negative e to the negative x times u, plus 1 minus x times e to the negative x times u prime. Cool so far? All right, so grouping the terms together, let's see what we're going to have. We're going to have x e to the negative x u double prime plus e to the negative x, I'm going to gather up all of the terms with u prime, minus x e to the negative x plus, distributing through here, e to the negative x minus x e to the negative x, all times u prime. And then working through in the same way with u, we will have negative e to the negative x, distributing through, we'll have minus e to the negative x plus xe to the negative x times u. And then simplifying further, let's see what we have. So we have x e to the negative x times u. If I factor out an e to the x on the right, I will have, well, we'll just do another line here. So I have 2e to the negative x's minus 2xe to the negative x times u prime. And then we'll have plus negative 2e to the negative x plus xe to the negative x times u. Oh, sorry, this one was u double prime. All right, so now if we factor out a 2e to the negative x, let's see what we'll have. We'll have plus 2, 1 minus x e to the negative x times u prime. And then over here, we will have plus, factoring out an e to the negative x, we'll have x minus 2 remaining, swapping the terms to make it pretty, and times u. Cool so far? All right, so now what do we want to do? We know that from the original differential equation that y double prime minus 2y prime plus y is equal to 0. So plugging in for y double prime, we'll plug in what we just got. We have xe to the negative x u double prime plus 2 times 1 minus x, that quantity, times e to the negative x u prime plus x minus 2, that quantity, times e to the negative x times u. And then minus, so this whole thing is y double prime, minus 2 times y prime. Y prime we did in blue, I think. Oh. And so we ended up with x e to the negative x u prime plus quantity 1 minus x e to the negative x times u. And then plus y. So when we're doing our original y, I believe that was u times xe to the negative x. All right, so, and that, of course, is all equal to 0. Okay, I did all this work over here and found out that I wrote the problem down wrong. So this is supposed to be a plus sign right here, plus 2y prime. So I'm going to change this to plus 2y prime, which is going to change the negative in front of the 2 to a plus. Cool, cool. Sorry about that. And then continuing, we will have xe to the negative x times u double prime, working with the coefficients to u prime, factoring out an e to the negative x. We'll have 2 times of these 1 minus x's. The next u prime is over here, plus 2x. That's times u prime. And then working with the coefficient, oh, and sorry, we have an e to the negative x there, times our u prime, plus, let's not forget about the 2. Now we're looking for the coefficients to the u, so we'll have x minus 2 from the purple, and then 2 1 minus x's from the blue, and this positive 2 we're multiplying it to, and then from the green we'll have an x, and that's all times e to the negative x u prime, and that's all equal to 0. And that's u, not u prime. All right, so we'll have xe to the negative x u double prime plus 2 minus 2x plus 2x times e to the negative x u prime plus x minus 2 plus 2 minus 2x plus x e to the negative x times u equals 0, and we will get x e to the negative x times u double prime plus 2e to the negative x, because the x is 0 out, that's times u prime, and then all of this over here will 0 out, so that will be equal to 0. Good so far? Perfect, perfect. And now let's go ahead and take a look at how this will look if we factor out an e to the negative x, because we know that can't be 0. That's where I'm going with this. So we'd have x u double prime plus 2u prime equal to 0. So that would give us e to the negative x is 0, which we know is extraneous, or xu double prime plus 2u prime is 0. And now I want a coefficient of 1 in front of the u double prime. So I basically divide through by x, and I will get the result of u double prime plus 2 over x times u prime is equal to 0. Good so far? Now we do a substitution here. We let w equal to u prime. So that'll give us w prime plus 2 over xw is equal to 0. Now this is linear in form, right? So my integrating factor is going to be e to the integral of 2 over x dx, which is equal to e to the 2 natural log absolute x, which is e to the natural log x squared, which is just x squared. Cool so far? So multiplying both sides by x squared, we will have x squared w prime plus 2xw is equal to 0. And then, as we intended to do, this will be equivalent to the derivative with respect to x of x squared times w is equal to 0. X squared dw is equal to 0 dx. We're going to keep that 0 dx so we can get our constant of integration. So this will give us, when we integrate both sides, we'll get x squared times w equals our constant of integration. Call it constant 1, if you will. And w will be equal to our constant 1 over x squared. But what was w? W was u prime. Just add another page here. So, continuing, we have w equals u prime. So u prime is equal to c1 over x squared. But u prime is du dx, which will be c1 over x squared. These are separable, so we'll have du is equal to c1 times 1 over x squared dx. Integrating both sides, we will have u is equal to c1 times natural log, times x to the negative 1 over negative 1, plus our second constant here, u would equal to some other constant, c3, because negative times a constant is still the negative, over x, plus some constant c2. So if I just kind of get the constants out of the way, do you see I'll have 1 over x times that c3 plus some constant c2. So now here, this can be part of my other answer, because y2, remember, is equal to my u, which I'll just call 1 over x, right? And then times xe to the negative x. And what is that? Beautiful. That is just equal to e to the negative x. And we're all done. Okay, so let's look at an example here where we not only need to find the a second solution, but we want to find a particular solution. So this one is non-homogeneous because it doesn't equal to 0. So now let's kind of go through this guy and see what we've got. So we can say that y is equal to u times y1, and that would make it u times 1, so y is just equal to u. And then when we find y prime, we're just going to get u prime, and then y double prime will be u double prime. Good so far? Okay, so now when we combine them together, we have y double prime plus y prime is 1. And so y double prime was just u double prime. And then y prime was u prime. And then those will equal to 1. If we let w equal to u prime, we'll have w prime plus w equals 1. This is linear in form, so our integrating factor is going to be 1 because that's the coefficient of the w. So we'll just get e to the x. Multiplying both sides by e to the x, we will have e to the x w prime plus e to the x w is equal to e to the x. This gives us d dx of e to the x times w, and that's still equal to e to the x. And now we'll have e to the x dw is equal to e to the x dx. Integrating both sides, e to the x, treated as a constant, times w is equal to e to the x plus some constant of integration, call it constant 1. And now isolating w, we need to, multiply both sides by e to the negative x. Be careful it doesn't drop off with the constant. And then that's going to give us 1 with that first multiplication plus c1e to the negative x. But what do I want? I want u. So remember that w was equal to u prime. So u prime, which is du dx, is equal to 1 plus c1e to the negative x. This is separable. So integrating both sides, we'll get u is equal to x minus c1e to the negative x plus some constant c2. So y2 at x is going to be equal to, and you can look and see what we had initially. We had a constant, right? So y2 at x we can have be equal to e to the negative x. And then the particular solution in terms of x is just going to be x. Okay, so now in general, the general case here. Remember how we started out with a2 at x times y double prime plus a1 at x times y prime plus a0 at x times y is equal to 0. Cool so far? Now, if we divide through by a2 at x, we'll end up with and we're going to assume, of course, a non-zero case for this coefficient. And we'll end up with y double prime plus, now we'll call a1 at x over a2 at x some p at x times y prime. And then a0 at x over a2 at x, we could call some q at x times y is equal to 0. And so p at x and q at x are continuous on some interval I. And we're going to also assume that y1 at x is a known solution. Of our favorite y double prime plus, now it's dressed up as p at x times y prime, and q at x times y equal to 0. We're going to also assume that y1 at x is not equal to 0 for every x in the interval. Now we do our substitution. Our substitution. Let y equal to u at x times y1 at x. And so we will have y prime is equal to, so we'll just shorten this, if y is u at x times y1 at x, we'll get y1 times u. Y prime is going to be y1 prime times u plus y1 times u prime, which is equal to, I'm just going to write it, commuted here, and then y double prime is going to be y1 prime u prime plus y1 u double prime, that's the first term, and then plus y1 double prime times u plus y1 prime plus u prime. Simplifying that one, we'll have y1 times u double prime plus 2 of these y1 primes u primes, and then y1 double prime times u. Good so far? Now putting them together, just like we did before, we just don't know them. We're getting a general formula. So we know that we started with our y double prime plus p times y prime plus q times y. That has to equal to 0. So y double prime was what we just got here, y1 u double prime plus 2 y1 prime u prime plus y1 double prime times u, and then plus p times y prime, which we did in the green, and y prime was y1 u prime plus y1 prime u, and then we have plus q times y, and y was, from way back in the beginning, y1 times u. That's all equal to 0. and matching up the u higher order derivative coefficients, we'll have y1 u double prime plus 2y1 prime, now I'm looking for the u primes, plus p y1, that's times u prime, and now the coefficients to the u terms. So we'll have y1 double prime plus p y1 prime plus q y1 all times u has to be 0. But what did we know? We know that y double prime plus p y prime plus q y has to be 0, right? From what we started with. I mean, yes, we're dealing with y1s, but that's okay. So this guy, all of this is 0. So this will simplify to be y1 u double prime plus 2y1 prime plus p y1 times u prime is 0. We do our trick and let w equal to u prime to reduce the order. We'll have y1 w prime plus 2y1 plus p y1 times w is equal to 0. Now we want to divide out the y1. Remember that not all of them were 0. And we'll have w prime plus 2, and my apologies, this is prime. There we go. 2 y1 prime over y1 times w. Actually, that's fine. We'll just write it like this. 2, and then the ratio of y1 prime over y1 plus p, all of that is times w, and that's equal to 0. Now, this is separable, right? We can rewrite this as w prime over w is equal to negative 2 y1 prime over y1 plus p, and then the negatives on the outside. Now, a little bit of trickery, right? So w prime is dw dx, right? So we're going to replace w prime with dw dx. That's over w. That's going to equal to negative 2 times dy1 over dx over y1 plus p. Now if I multiply both sides of this by dx, because it is separable, then on the left hand side I'll just get dw over w. On the right hand side I'm going to get negative 2 dy1 over y1, because that dx divides out, and then plus p dx. So it's distributing to both. And so when I integrate, now what's going to happen? Well, I'll get natural log absolute w is equal to negative 2 natural log absolute y1, because now I'm integrating y1 with respect to y1, right? Or I'm integrating 1 over y1 with respect to y1. And then I'll still have, and remember, I apologize, the minus was inside or on the outside. So that minus will go to the integral of p dx. So now I can get some stuff together. We'll have natural log absolute w is equal to natural log y squared minus the integral of p dx. And my minus is still here. I'm going to add that natural log to both sides, and then I can use properties of logs to bring them together. And then I have my constant of integration going on here. And we'll have, this is negative integral p dx plus c. And now this will be equivalent to wy squared is equal to e to the negative integral p dx plus c. So wy squared will be, again, that trick with the constants, we can call this c1, e to the negative integral p dx. But don't forget that w was equal to u prime, right? So we do have our w is equal to c1 times e to the negative integral p dx over y squared. But now, going back to w being equal to u prime, we'll have c1 e to the negative integral p dx over y squared. And I think I lost my y1. My apologies. These should be y1s. y1s. Perfect. Okay, so u prime, of course, is du dx equals to c1 e to the negative integral p dx over y1 squared. So du will be c1 e to the negative integral p dx over y1 squared. And then we'll integrate both sides. We can bring the constant c1 outside of the integral with respect to x on the right side. So we get u is equal to c1. And then we'll have our integral e to the negative integral p dx over y1 squared dx, and then we'll have plus some other constant, call it c2. Okay, so now to finish it off, we want to find our y2. So if we let c1 be 1 and c2 be 0, remember that y was equal to, so that will be our y2 at x, right? And that was equal to y1 at x times u at x, right? So y2 at x will be equal to y1 at x times the integral of e to the negative integral of p at x dx. y1 at x squared with respect to x. So here's a cool, groovy formula a person can use instead of working it out, crunching it out like we had done before. Now, the next example is an application of how we can use this formula, because it's really useful to use, especially when you end up with an integral that we can't find, by regular methods. So here we go. First step, of course, is to get a coefficient of 1 in front of the y double prime. So we're going to divide both sides by 2x. And y1 at x is e to the x. So using just one side of the constants, all the constants you can use for solutions and etc., we can say that x0 is greater than or equal to 0. Okay, so this will give us y double prime minus, I'll actually do a plus, and then we'll have negative 1 minus 1 over 2x when I bring that 2x inside, times y prime, plus 1 over 2x times y is equal to 0. So now we want to identify what our p of x is. So our p of x is the coefficient to the y prime term, and I'm going to go ahead and factor out a negative, and I'll have 1 plus 1 over 2x. And so, using our formula, y2 at x is equal to y1 at x times the integral of e to the negative integral p at x dx divided by y1 at x squared, that quantity squared dx. So with this one, we know we're defining this in terms of an integral defined function. So let's start with that. We're going to have y2 at t is going to be equal to y1 at t times the integral from x0 to x of e to the negative integral p at t dt over y1 at t, the quantity squared, all with respect to t. So, plugging in what we know, we'll have y2 at t equals y1 at t will be e to the t. We'll still have that integral from some x0 to x, e to the negative, so negative, because p at x is negative 1 plus 1 over 2x, so p at t will be negative 1 plus 1 over 2t. The negative will cancel each other out, so we'll have the integral of 1 plus 1 over 2t dt over e to the t squared, all with respect to t. Continuing, we have e to the t times the integral x0 to x. This integral here is going to be e raised to the t. Now, 1 over 2t is the same as 1/2 times 1 over t. So we'll have 1/2 natural log t. x0 is greater than or equal to 0. So t must be greater than or equal to 0. So we don't need our absolute value. That's going to be over e to the 2t, all with respect to t. And continuing, y2 at t will be e to the t integral x to the 0 to x. This will be e to the t times e to the natural log of the square root of t. Working on a little algebra there. When you're adding the expression within, adding the exponents, it's the same as the product of the same bases. And then we have our e to the 2t down here and dt. And it's cleaning itself up here. This is going to be e to the t integral x0 to x. And then e to the t divided by e to the 2t is e to the negative t. E raised to the natural log root t, we'll get root t, and then dt. And then we want to say that x0 is greater than or equal to 0. And we got our result. All right, perfect. So I hope you had a wonderful morning, afternoon, or evening whenever you're watching this show. If you like what I'm doing, hey, click that subscribe button and that like button. Bye.